now that we've completed our beam and shell analysis of this part, I'd like to share something really nice with you about Ansys's capabilities in this area. We can take this and do what we call a shell to solid and beam to solid submodel. So let's say that we cared about the details of some of these joints here where the beams come in and meet the shells in this model. Ansys makes it very easy to do a solid submodel based on that from that connection using this as our course model. So let's go through and set that up. The first step is to come back to the project schematic here. And what we want to do is place a new static structural analysis onto the project schematic and call this our submodel. Okay, now I'm going to say I want to use the same engineering data with material data, link that right across. And what I'm going to do is use a geometry that I've previously prepared, which basically takes the model that we had before and cuts out just the sections that have joints that we care about. So those will now be represented as solids, whereas before they were the beams and the shells. The last step here on the project schematic is to say that I'd like to map solution information out of our original model, our course model, into our submodel, and that's going to be represented by this link here. Okay, so we're all set up from the project schematics point of view. Let's dive into mechanical and set it up. The first thing we notice when we come in is that our solids have been brought in now, and again, these are no longer beams and shells. These are actual solid bodies. Okay, now they come in as separate solid bodies, but I want to point out that mechanical has used automatic contact generation to generate contact regions that are necessary to hold all these together, and there's no modification necessary in this case. It's done a really nice job of picking all the faces that are in contact and setting them as bonded, so that the natural bonded behavior is taken care of. So besides contact, let's work on the mesh here. Now, what we can do is a little different than in the shell and solid. We want to give it a finer mesh. This is a submodel. So I'm going to ask for a uniform mesh. I'd like the relevance center to be fine here. And let's go in a little bit finer than we did before and give it something like 10 millimeter minimum and a 15 millimeter maximum. One more step. I want to make sure that we use a certain method on these parts. These are bodies that on their own naturally would not be sweepable, but we have a powerful mesh method that will allow us to generate some really high quality hex elements on this called the multi-zone mesh method. So let's use that. So I'm going to select all bodies actually in this entire analysis and ask to please use the multi-zone method. And let's generate our mesh here. So the mesh that's generated here, let's take a quick look at the quality. First of all, it's about 150,000 nodes. That's just fine. And if we look at element quality here, we see a pure hex 20 mesh, minimum 0.5. That's a fantastic quality mesh, really, really off the charts. So we're doing really well mesh-wise here. Next, let's set up our mapping for submodeling. So this object has been placed in the tree for us, coming from the previous analysis, stating that the Workbench project schematic knew we were doing a submodeling analysis, and it's going to pipe that data right in here. Let's start off with the beams. So I want to insert a type of submodeling. We're going to use a cut boundary remote constraint. Okay, so to do that, it's going to ask us which faces of these solids correspond to the beams that we would like to map the data from. So it's going to be the top of each one of these 8 beams that we're analyzing here. So I'm going to go in and select one. Let me go over to a face selector here. And I'm going to ask to create a name selection so I can get all of them. So we're going to call this beam tops. And I'm going to ask it to please apply to all geometry of the same location in the Z. Let's see what it comes up with when we do so. Great, came up with 8 faces sitting there ready for us to use. Beam tops name selection. Let's come back into this object here and say don't use a geometry selection. Use beam tops, the name selection here. Everything else in here is set. It's a transfer of a beam to shell solid. Let's import it and see what it does. What we've got upon importing is 8 remote displacements have come in, and these remote displacements correspond to what the beams from the beam and shell model, the course model, we're seeing. So these orientations and these directions are showing us basically what the deformations of the beams were at that point, and it's being applied via remote displacement to replicate that behavior directly onto the solids. A really nice capability to do beam to solid submodeling. Now that we've got the beam set, let's go work on our shells. So I'm going to ask for a regular cut boundary constraint now, and it's going to ask me to pick the faces that I'm going to map the data on for the submodel. Now again, I'm picking the faces here that had enforced constraints in the larger course model. Okay, that's the idea. So I know which faces that needs to be. It needs to basically be these outside faces. I'm going to pick all of them here. Okay, we can flip around and do the other side. We should get 8 more now. And then there were a couple based on the way that I had cut this up earlier that we also need to include. We've got to include these here, and then this guy right there. And we've got 22 faces selected, and these are our guys that we're going to apply the boundaries from. So let's go ahead and import that load. And we see our displacements have been mapped over from the old analysis, the course analysis, onto this submodel. So we should be set to go at this point. We've got our beams mapping into all of these, and we've got our shells mapping onto these solids, and we're ready to ask for a solution. Once we've got the solution here, we can go ahead and ask for deformation and stress, evaluate those, and we should notice contours and values that look similar to what we saw in the course model. So let's take a quick look at that and see if it matches up. We've got a maximum displacement around here of about 9.3. Okay, it should be a little bigger in this one because the displacement max for this was elsewhere, but we can see we're clearly in the right ballpark here, so I feel good about our submodel. Same for the stress. Let's take a look at the comparative values here and see what we've got. So when we come in now and we zoom and we look, we're seeing a detailed 3D submodel of this section. And we can tell right off the bat, this looks about right. And we can go in and do further analysis, maybe add a fillet in here to get a more realistic distribution of stress around, whatever we want to do. But the idea here is that thanks to the Workbench project schematic and the workflow that it facilitates, we're able to take this beam and shell model, submodel nicely into a detailed solid model.